Topological sort. Topological sort is a method of arranging the vertices in a directed cyclical graph or DAG as a sequence such that no vertex appear in the sequence before its predecessor. It is a linear ordering of its vertices such that for every directed edge UV from vertex U to vertex V, U comes before V in the ordering. For instance, vertices of the graph may represent tasks to be performed, and the edges may represent constraints or something that limits or restricts that one task must be performed before another. In this application, the topological order of the digraph is just a valid sequence for the task. So, for it to be possible, the graph should be no directed cycles, or it is only possible if and only if the graph has no directed cycles, that is, if it is a directed acyclical graph. So a directed cycle, as you can see, has a back edge wherein the vertex, for example, vertex A is directed to the vertex B, and vertex B is directed to vertex A. So in a directed acyclical graph, it has no cycle, as you can see. Okay, for example, consider a set of 5 required courses, C1, C2, C3, C4, and C5. A part-time student has to take in some degree program. The courses can be taken in any order as long as the following course prerequisites are met. C1 and C2 have no prerequisites. C3 requires C1 and C2. C4 requires C3, and C5 requires C3 and C4. The student can only take one course per term. In which order should the student take the courses? So this is the diagram representing the prerequisite structure of 5 courses. So C1 and C2 have no prerequisite. C3 requires C1 and C2. Then C4 requires C3. C5 requires C3. C5 requires C4. The first algorithm to solve this topological sorting problem is based on a direct implementation of the decrease and conquer technique. Repeatedly identify in a remaining graph and in a remaining digraph a source which is a vertex with no incoming edges, and delete it along with all the edges outgoing from it. If there are several sources, break the tie arbitrarily or without you taking too much time in choosing. If there are no vertex with no incoming edges, stop, because the problem cannot be solved, or just means that it is not a directed cyclical graph. Source removal. This is a simulation. On each iteration, a vertex with no incoming edges is deleted from the diagram. So in here, we have C1 and C2. We can take C1 or C2 first, but okay, we'll start with C1. And then C2, then C3, C4, C5. This is now our topological order of the graph. Okay, DFS-based topological sorting. The second algorithm is a simple application of DFS, or depth first search. First, perform a DFS reversal and note the order in which vertices become dead ends. Then, reversing this order yields a solution to the topological sorting problem, provided, of course, no back edge has been encountered during the reversal, which is stated earlier that if it encountered back edge, the digraph is not a DAG, and it is impossible to have topological sorting. Okay, this is the illustration of topological sorting using DFS. First, we'll DFS traversal. We'll insert C1 to the stock, followed by C3, then C4, C5, and then since it's a dead end, so we will pop this element, and then we'll go back to C4 since it's a dead end and it has no incoming or outgoing edge, so it will be popped to, then C3, then C1, and the unvisited one is C2, which has no incoming edges, will be inserted to the stock and it will be popped. And the order of these, we'll just reverse this and we will get the topological order of the graph. Source removal order has C1 first and then C2, and in here C2 first and C1. It is both correct because C1 and C2 have no incoming edges, so you can start in either of these. Algorithm. First, color all vertices white. It means it is unvisited. Then initialize an empty stock S. While there is still a white vertex U, this loop will go on. Okay. First element is A. It will turn to gray. Then V active to be U. And then V active as it will check if V active has a white neighbor V, which is its adjacent node B, and then it will be color gray, means color gray means it is visited, but its neighbor is not yet finished, or it is not a dead end. So okay, we will now insert V active to S, then V active now is B, and then V active is B, so its neighbor is C. We'll go again, and then B, then now E. V active is now E, so it will check if it has white neighbor V. So because it is a dead end, so it will go to S. It will be color block. Block means it is a dead end. So we will pop the top vertex of S and set it to V active. So V active is now D, should be, which last inserted in the stock, because it is a stock, last in first out. So okay, it will be so it will go again if V active has a white neighbor. This false, so else this will turn to block. Then C will check again since it has no white neighbor, so it will be block. And then B, then A. Okay, so now V active is null because stock is now empty, so the loop will stop. Okay, the order of the nodes that turn black is E, D, C, B, A. So to get the topological order, we will reverse this and we will get A, B, C, D, and E. For the running time, so In initializing in degree array, we have O of E or O of edge, and then initializing Q with in degree 0 vertices is O of V or O of vertices, and the Q and output vertex each takes only one to the Q and output, so total time will be O of V. Reduce in degree of all vertices adjacent to vertex and in Q any in degree 0 vertices. Total time is O of E. So the total time O of V, O of the absolute value of V plus the absolute value of E. So this is the linear running time.